Hey, Visca the teacher, here. Good to have you back over there, wherever you might be, on a bus, with your cell phone, watching this, at home, in the classroom, when you really should be paying attention to your teacher, but you got this streaming. Either way, it's all good, because you are interested in calculus, and today we are going to go over the 2017 Calculus AB exam. We're going to continue it. We are in Section 1, Part B, which is the multiple choice questions. We are going to do problems 84 through 90. And, you know, it's comforting to know that we get to use a graphing calculator, but for some of the questions. Because even though you get to use the graphing calculator for this entire part, Section 1B, not every question you can use the calculator to get the answer, if that makes sense. We discussed that in problems 76 through 83, or something like that. Who knows? Who knows what it was? Well, let's finish this off. Number 84. The number of bacteria in a container increases at the rate of RT. It is important to know, okay, that RT is a rate. Okay, that's bacteria per hour. If there are 1,000 bacteria at time 0, okay, that is also important to know. Which of the following expressions gives the number of bacteria in the container at time 3? So we're looking for the number of bacteria. Okay, we no longer need a rate. We have a rate. We want to end up with an actual number, which means I need to integrate my rate to get my number, okay? My rate is RT. So, you know what am I doing? Why am I not using the calligraphy pen? It's so much cooler, okay? So I need to integrate my rate, RT dt, okay, at time 3. So from 0 to 3, I want to add up all of this. You know, integration is area under the curve. I'm going to add up all those values and get a number from the rate, all right? So I know it has to have an integral in it. It can't be A or B, maybe C, but look, this has this here as well. So the million-dollar question is, which one is it? What I underlined in green, 1,000 bacteria at time 0. Before I even started with the rate, I already had 1,000 in there. So I want to make sure I include that 1,000 and then add it. Because at time 3, I'm going to have all of these plus the 1,000 I started with, choice D. 85. The function g is continuous on the closed interval from 1 to 4, with g of 1 equaling 5 and g of 4 equal to 8. Of the following conditions, which would guarantee that there is a number c in the open interval from 1 to 4, where g prime of c is 1. So there's a number that if I take the derivative of it, right at that number, it should equal 1. Okay, what sticks out to me the most, because some of these problems can be a little bit confusing, but all right, let's look at A. A says g is increasing on the closed interval. Just because it's increasing all the way from 1 to 4, does not guarantee, okay, that there is some value where it's equal to 1, okay? Choice B, g is differentiable on the open interval from 1 to 4. Well, I tell you what, if it's continuous, that doesn't mean it's differentiable. I can have a corner, I can have a cusp, I can have a vertical tangent line. These are all continuous, but they are not differentiable. If you tell me it's differentiable, then I know that every point has a derivative or a slope. Okay, so I like that. It's not A. Okay, g has a maximum value on the closed interval. That doesn't guarantee anything. And the graph of g has at least one horizontal tangent line. That guarantees nothing as well. So it is B. And you might say, yeah, but, okay, this guarantees that there's a derivative somewhere. But what about the 1? change in y over change in x. You must train your brain to realize these are coordinates. 1, 5, 4, 8. So if I do my change in y over my change in x's, 8 minus 5 over 4 minus 1, that is 3 over 3. That's where my 1 comes from. That's where my 1 comes from. All right? It's one of those theorems, intermediate value theorem, something like that. I don't know. But if the slope between my 2 points is 1, okay, and this is where the answer comes clear. If the slope between my 2 points is 1, let's say I have 2 lines right here, and let's say that slope is 1. If I have a continuous line that's differentiable everywhere, that guarantees me that at least at one point in between those two endpoints, I have to also have a slope of 1, which means if I go somewhere, maybe here at this point, it has to also be 1. Maybe here at this point, okay? There has to be at least one point that's equal to 1. And oh, by the way, there's no corners or cusps because it's differentiable everywhere. You're welcome. The twice differentiable functions f, g, and h have second derivatives given above. So we have the second derivative of f, the second derivative of g, and the second derivative of h, all in question 86. Which of the functions f, g, and h have a graph with exactly 2 inflection points? Inflection points means we're going to look where the second derivative is equal to 0, and, okay, it's going to change from positive to negative or from negative to positive, because that's going to change the concavity. I make it simple in my class. I say my smiley faces and my sad faces. If it's plus to minus, it's going to change from happy to sad. That's my inflection point, okay? If it's minus to plus or negative to positive, it's going to go sad to happy. That's my inflection point. So what I'm going to do, because we get the calculator in this section, yeah, man, I'm going to graph all 3 of those. And I'm going to kind of cheat when I graph this, because that's kind of a lot of typing to put in a calculator. I'm going to put this right here into y1. Okay, this is going to go into y1. And then in y2, notice that this is exactly the same. So I'm going to cheat. And in y2, I'm going to actually put the variable y1, which is what's in this blue box, and then I'm just going to put a +1 after it, so I don't have to type. And then for y3, because I'm going to put all 3 graphs in the same line, I'm going to do the same thing. I'm going to put y1, because this is y1, and then I'm going to put -1 after that. Okay? So if you're still trying to figure out what the heck I'm talking about, let me show you. Turn this on. On. I'm going to go to y equals. And I'm going to put in y1, I've color coordinated these, the blue box, x times x minus 1 squared, all right, times x plus 2 cubed. All right? Now, I can type all of that and put a +1 at the end, like what's in the red kind of box up there. Or I could just go to vars, y variables, and just say, I want y1 exactly as it is, but I'm just going to add 1 at the end of it. And for the next one, I'm going to do the same thing. I still want y1, but now I'm going to have a -1 after it. And I'm going to graph that. Okay? So we are going to use our graph. We're going to evaluate our graph. There's f double prime, the blue. Okay? We're going to evaluate these graphs, and we're going to see, based on the graph, there's g double prime. And then we're going to see how many times this changes. Okay, concavity. And there's my last one. All right, kind of looks like a little bit of a mess. So I'm going to zoom in a little bit. All right? And I'm going to hit zoom. My favorite type of zoom is the box. Well, let's go out here. Go up here. I really don't need these peaks. I really just need the x-axis. Just going to go across like that. Some of you guys might want to see everything, so we'll do this. Boom. I'm going to zoom right in there. And everything's going to be nice and neat. I'm going to pull this screenshot onto our background. I'm going to use some highlighters to kind of help us determine what is what. You know how much I love using highlighters. So as soon as this gets done, and you can now see the separation clearly between the red line, the blue line, and the black line. So, and that's really going to help us when we determine the answer to this question. All right, here we go. Bring this out here. So, remember, I want to see where my second derivative changes from positive to negative. But I want 2 points of inflection only. Exactly 2 points of inflection. Now, these graphs are the second derivatives, okay, of f, of g, and of h. Now, if the y value, I'm just going to say f double prime. If the y value is the second derivative, aren't all the y values positive when I'm above the x-axis, and all the y values are negative when I'm below? They are, Mr. Visca. Thank you. That means if the y values are positive above the x-axis, the second derivative is positive whenever the graph is above the x-axis. Okay? If the y's are negative when you're below the x-axis, if I have negative y's, that means I have negative second derivatives. Okay? Same thing, if the y's are positive up here, that means my second derivative is positive when I'm above the x-axis. So let's go ahead and now determine, we'll do f double prime, the blue one. Here's my highlighters. It's my time to shine. Don't mess it up. All right, so I'm the blue line. The green represents positive. Okay, then it dips below, and this purple now represents negative value for second derivative. Then it comes above and becomes positive again. It hits the x-axis, but it never goes below. So the sign doesn't change. So what that tells me is there are 2 points where I change, right there and right there. So my blue line, which I just went over, does have 2 inflection points. So F is an answer. So it can't be this one or this one. G is in both of these. So I only need to look at H. Is H an answer? If it is, okay, then D's the choice. If it is not, then I pick C. So right now, this is, and by default, I know G. G is in both of my correct answers. So I'm not even going to check the red one. So let's go right to the black line, which is H double prime. All right? I'm going to use my highlighters again. Oh, what a beautiful, not the crayon. What a beautiful little morning. All these highlights. The black line is positive. Then the black line is below the x-axis, so the y's, or second derivative, are negative here. Ooh, then it goes back above, and it's positive y values, or positive second derivatives. Then it falls below and negative. Oh, my goodness. Then it goes back above. All right? So when I'm looking at this, how many times does it change from positive to negative, or negative to positive? Well, let's go here. Let's go here. Let's pick yellow because it really pops. 1, 2, 3, 4 times. I mean, if it said at least 2, that's fine, but it says exactly 2. Okay, so H, we're not picking. We're not picking H. Our answer is C. It's just F and G have exactly 2. That's a really good problem. Number 87. The table above gives values of a function f at selected values of x. If f is twice differentiable on the interval from 1 to 5, when x is greater than or equal to 1 or less than or equal to 5, which of the following statements could be true? All right, I'm just going to plot these. I could sketch these out, but we have the calculator. Why not use it? I'm going to clear this out. Hit second plus 712. That resets everything. I'm going to go to stat, edit. I'm going to put my x's in my L1 column. So it's 1, 2, 3, 4, and 5. And I'm going to put my y values, or the f of x, in the L2. 9, 4, 0, -3, -5. Now, if I want my graph to just plot these points without drawing a line, when I go to y equals, I'm going to clear this out, clear this out, clear this out. I'm going to go up to plot 1 and hit enter. Now when I get off that, you see it's highlighted. All right? When I hit my graph, didn't I just hit second plus 712? Maybe I messed that up myself. So let's just do a zoom standard, which is 6. And there are our points. So I'm going to bring this out here. Right there. Now if I connected these, it kind of comes down like this, and it's starting to curve. You see how it's starting to curve? It would probably imagine to continue like that. So they're asking if f prime, which is the derivative or slope of f, is negative or positive. So first I'm going to eliminate some things. This is a downward movement, so it is negative. And you can tell the y values just drop. So it's moving downward. So it is negative. It is not positive, so it's not C or D. If f prime, okay, for A and B, if we're talking about f prime, is negative, and it's either decreasing or increasing, this is a rate of f prime. And a rate is the same thing as the slope of f prime. So I can just say it's the slope of f prime, which is also the second derivative, which is concavity. If it's increasing or positive, it's going to be a smiley face. If it's decreasing or negative, it would be a sad face. So which one of these, does it look like it curves where it bows down, or does it curve bowing up? No, it doesn't look like that. If I do this, I mean, it kind of resembles more a curve up. So it's definitely a smiley face, so it should be increasing, not decreasing. It's not sad. Oh my God, it's happy. Good deal. We're doing well. 88 says, let f be the function defined by f of x equals the ln of x squared plus 1, and let g be the function defined by g of x equals x to the 5th plus x cubed. The line tangent to the graph of f at x equals 2 is parallel, that's an important word, to the line tangent to the graph of g at the point where x equals a, where a is a positive constant. What is the value of a? We know what we need to solve for. Okay? I know that the line of f at 2 is parallel to the line at g where x equals a. Parallel means that the slopes are the same. And this is calculus, so we are going to say the derivatives are the same. All right? So I need to take the derivative of this at x equals 2. Okay? When I find the derivative at 2, that should be the same or equal. Slope same means derivatives are equal to the slope or derivative of g at some value a. And we're just trying to find out what value would make it equal to whatever number that is. Again, this is calculator town, people. You in calculator town. You best know how to use this calculator. So I'm going to turn this on. All right, let's get out of here. And I'm going to go to Math 8. And I'm using x as my variable. I'm going to put the equation that I want to take the derivative of in the parentheses. So many kids will try and take the derivative of that ln function and put the derivative in there. No, 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 no. The calculator is going to do that for us. So it is the ln of x squared plus 1. All right, and I want that when x is equal to 2. And if we do that right, 0.800000000. If I have to round 3 decimal places, I'm just going to call that 0.8, if you don't mind. All right? So I go here. So this is equal to 0.8. Now, I don't know what this number is. But if I look at g, I can definitely take the derivative of that. That's really easy. That is 5x to the fourth plus 3x squared. So remember, a is going in for x, correct? So I'm really just finding out what value of x in this equation here would be 0.8. I'm going to put this in y1, and I'm going to put this in y2, and I'm just going to see where they intersect. Guess what? It might be at multiple points. But my value that I'm looking for, x, which they call a, is going to be positive. So if you get a negative and a positive, you want the positive answer. All right? And again, we're going to use our graphing calculator. Y equals. Let's get rid of this plot. I'm just going to go up there and hit enter so it's not highlighted anymore. 0.8 is equal to 5x to the fourth plus 3x squared. And I'm going to graph that. And there's our graph. All right? Well, they intersect at 2 points here and here. This value on the x is going to be a negative x. Remember, I only want the positive one, so I'm not even going to check this one. I'm going to just find that intersection point right there. And in order to do that, I go to second trace, and I want the intersection, which is 5. And I just put my little spider dude close to the intersection. That's what I call that thing, spider dude. And I hit enter 3 times. And I get this 0.447. That 7 will stay a 7. It will not round. And right here, 0.447. Right there. Good to go. 89. Only 2 more problems. We're going through this rather quickly. Nice. Let f be a continuous function for all real numbers. Let g be the function defined by g of x equals the integral from 1 to x of f of t dt. If the average rate of change of g on the interval from 2 to 5 is 6, okay, average rate of change is the slope, the average slope, okay, which of the following statements must be true? First of all, we don't know anything about the slope right at 2 is 6. That's poo-poo. Okay? This is not finding the derivative or slope of g. That's actually going to what g would be the derivative of, which is weird. It's not this one. Okay? It's not that one either. Okay? So it's either A or C. And average slope, okay, if I want to do the slope, this averages the 2 numbers, because I'm dividing by 2. But if I want the average slope across that interval has a difference of 3. That's the way I look at that. Okay, so by default, I'm going to pick A, which is the answer. But I'm going to show you something else here. Okay? If g of x is the integral from 1 to x, right, of f of t dt. First of all, it immediately jumps out to me that we got an x here and t's here. All right? So they say that the average slope or rate of change of g from 2 to 5 is 6. So if I take the derivative of this side, I'm going to take the derivative of this side as well. All right? I'm going to balance both sides. All right? So now I've got g prime of x equals, okay, if I take the derivative of an integral, they kind of cancel because they're kind of opposites. And what happens is my x just goes in and replaces this. The dummy variable goes bye-bye with the integral. So now it equals f of x. So f of x is g prime. Let me state that one more time before I connect this all together. F of x is g prime. So if the average value from 2 to 5 is 6, well, f is this, which means it's the same, which means the average value from 2 to 5 of f of x is 6, because the average value from 2 to 5 is 6 of g prime, and f is g prime. Badoosh. I like it. I like it a lot. All right, let's finish this strong, people. Number 90. For any function f, which of the following statements must, not can, must be true? Okay? Choice 3, choice 1 and 2, choice 2 and 3, or all 1, 2, and 3. Wow, we have the whole gamut there, except 1 and 3, but who puts 1 and 3 together? Anyways, choice 1, if f is defined at x equals a, okay, then the limit as x approaches a of f of x is f of a. This is how you determine continuity. Okay, the limit has to equal the actual coordinate. So what it's saying is if f is defined, if there's an actual point, okay, at where x is equal to a, then the limit has to equal the point. That is not true. That is false. Okay, it can be true. Okay, so it's not a must be true. Meaning, here's where x equals a, right there. And I have this line, okay, and it goes like this. But what if I have a hole here? Okay? Okay, the limit as I approach this, I'm just going to pick some number. Maybe it's 3. Okay? But the actual coordinate is removed, and it's right there. So the limit as x approaches a, well, that's 3. But f of a is 5. Okay? So this isn't an absolute have to be true. It is definitely not an absolute have to be true thing. Now, let's look at choice 2. If f is continuous at x equals a, then the limit of f of x as x approaches a is f of a. Yeah, this is how you define continuity. So if it's continuous, this has to be true. And I'm going to go back to my little diagram here. If this is continuous, that hole will be filled in, which means this would be right where the hole is. And then, yeah, then this would be 3. That's how you define continuity. This is absolutely true. And 3, if f is differentiable at x equals a, then f of x equals f, the limit as x approaches a of f of x equals f of a. This is a little dig at your brain here, because if it's differentiable, it has to be continuous as well. The other way, not true. It can be continuous and not differentiable. Corner, cusp, vertical tangent line. All right? But if it's differentiable, it has to be continuous. It's basically the same thing as 2. So that is true. So it's 2 and 3. The answer is C. And we are done. I'm going to do another video where we go over the short answer. Everything's going to be lovely. It's going to be fine. I know you like these videos. I know you like them. Ring that bell. Come on. You won't. You won't ring that bell. You won't subscribe. I'm kidding. Ring the bell if you liked it. Subscribe. I like seeing you here. And I will see you again when we do the short answers.